So this is one of the common questions in A levels. How to do this question? He says that you have to start the comparison with the stress with stress. So the formula for stress in physics we have force over area, right? And he says that there needs to be a 1/10 size in dimension. So what does that mean? It means that in real life, if this crane, let's say, spans to 50 meters, if we make this in the laboratory, this is going to be only 5 meters. So everything is going to be divided by 10. All linear dimensions will be divided by 10. So let's compare. So let's compare what those dimensions are. So we can see that over here the load connected over here is going to have, let's say, certain dimensions. Let's say those dimensions are x, x, and x. So what you're doing is you're reducing every dimension by 10. So this cube actually now becomes smaller with x by 10, x by 10 width, and then x by 10 breadth. So the formula for mass in terms of density is equal to mass over volume. Take volume on the side, we have mass is equal to density multiplied by volume. Now, density does not change for a material. If you're using an iron block in real life, then we'll be using an iron piece in this real life. So it all comes down to the volume. So we can realize that in this situation, the volume was x, 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 which came out as x cubed. What has happened in this situation? So this becomes volume is equal to x by 10 multiplied by x by 10 multiplied by x by 10, which becomes x cubed by 1000, which means that the volume has been reduced by 1000, so the mass would also have reduced by 1000. And since in stress we are dealing with force, and force in this situation is the weight, so this is mg. If you are decreasing the linear length by 10, then the mass has also decreased by 1000, so the weight has also decreased by a factor of 1000. So in a real situation, if we compare stress, that would actually be force by cross-sectional area. This is my real life case, nothing was different. But in the model, what has happened for the case of the model, we realize that the force has been divided by 1000. Why? Because linear dimensions changed. Okay, the force has been divided by 1000. What's happened to area? Now area is equal to pi r square. Okay, now pi r square means that if the original diameter of the string was r, then the current diameter for the model is going to be actually r by 10. So this becomes pi r by 10 whole square, which becomes pi r square by 100, which means that for the model in the laboratory, the area should be decreased 100 times. The force will be reduced 1000 times and the area will be reduced 100 times. Now for this, we have stress for the model is actually F by 1000 divided by area divided by 100. Now since we're comparing real life with the model, real life divided by the model stress, so we are just going to replace the variables in this situation. We realize that we get F over A divided by F divided by 1000 divided by area divided by 100. So if you perform simple algebra, you will land at an answer of 10. Of course, because F over A and F over A is going to get cancelled out. If you find this difficult, let me show you this on how to do this on a calculator. So in place of F and A, I'm replacing 1 by 1 divided by 1 divided by 1000 and then 1 divided by 100 and see what the answer is going to be. Now to do this, I'm going to simplify this one as 1 divided by this 1 over 1000 will be written down as 1 divided by 1000 divided by 1 divided by 100 on the calculator, so that you can see that instead of performing this algebra manually, you can do this with a calculator as well. Let me show you how to do that. So let me make the equation right in front of you. We're using the fraction symbol. I write 1 because I know 1 divided by 1 in this area is going to be 1. So I come down over here. I make the fraction again. So I'm going to write down 1 divided by 1000. That is for this one as F by 1000 as this one. Over here as 1 divided by 100. Now when I press equals to, I get the answer of 10, which is what I simplified to this one. So in this case, the option will be option B. I hope you understand how we can use the calculator to perform this algebra. Now this is an interesting question in terms of strain and stress. You will notice that in this question, he will not talk about stress. Why? Because the area of cross-section is uniform and the load is same. So that means that even in the new situation or the old situation, the stress, which is F over A, is going to be exactly the same for all situations. What is happening with x? So he says that the length of y is 1 meter, the length of x is 3 meters, and then he asks you what will happen if the load is hung. What has happened is that this x has stretched by 1.5 millimeters and the y has stretched by 1 millimeters. What is this information? This information is basically about strain. So strain was change in length, delta x divided by length. Now for x, we find that the strain is actually 1.5 millimeters divided by 3 meters. And for y, this is 1 millimeters divided by 1 meter. So this actually comes out as 1 over 2 millimeters per meter. And this comes out as 1 millimeter per meter. What does that mean? That for every meter of length, this wire will stretch half a millimeter. And for every meter of length, y will stretch 1 millimeters. Now he says that a new section of wire is prepared that has 1 meter of x and 3 meters of y. So if we make this situation again, we have 1 meter of x. So the length of total x is 1 meters. And from this point onwards, we have y that has a length of, this is y, and has a length of 3 meters. Now we know that y stretches a bit more because this stretches 0.5, this stretches 1 millimeters. So this 1 meter length will stretch by 0.5 millimeters because of this strain that remains constant. And this one will stretch by 3 millimeters because we know that the ratio came out this way, that 1 millimeter will be stretched ratio of 1 meter if the length is 1 meter. So for a 3 meter length, it will stretch by 3 millimeters. And for this one, we realize if we open this up, this actually looks like for x, the change in length ratio length is actually 0.5 millimeters ratio 1 meter. This is what this number represents. So it will stretch 0.5 if its length is 1 meter. So it is already 1 meter. It will stretch by 0.5. So the total extension from the very beginning up to this point, from this point to this point, will be 3.5 millimeters. So the correct answer is option B. You can try this question on your own as well. It's your choice. We come to this point. This is just lengthy and you're going to miss some points, so we're going to discuss them right now. So a lift is supported by 2 steel cables length of 20 meters. So we have steel cables of 20 meters length, 20 meter length, and 2 steel cables are there. Each cable consists of 100 parallel steel wires. So each cable has 100 strands of wires. So I can say that the total strands will be 2 multiplied by 100. I have 200 strands available. Now it says that each wire has an area of this one and the Young model is this one. He says what's going to happen if a 70 kg man steps on this lift. For example, if the lift is over here, this is the platform, and a man walks by and stands on the lift, what's going to happen to the extension? Most definitely they will be extended, but let's see how to solve this. So we have Young's modulus equals to FL over AE, or extension. I have the value of Young's modulus, which is given to me as 2.1 power 11. So I'm going to replace the values and see what happens. So 10 raised to power 11 equals to, we have to be clever about the force. The length is 20 meters as given in the question, which is this one. So every strand, I assume, will have the same length, divided by the cross-sectional area of each wire is also given to us, 3.2 power minus 6. So 3.2 into 10 raised to power minus 6. I'm replacing this as A. Extension is what we need to find out, which is still required by the question. So how to put in the force? What will be the value of force? Now notice that in previous questions when we were solving, we understood that in these situations, if we have parallel springs or parallel wires, the load actually divides. So what's going to happen over here? If we have 100 different strands and 200 different strands, that means that the load is going to be divided onto 200 wires individually. So this 70 kg first has to be converted into newtons by using the formula mg, and that will be divided by 200. So be careful. Over here we'll put 70 multiplied by 9.81, then divided by 200, because this force will be divided among all 200 strands equally. So we are only looking for just one wire. This is the area of one wire. This is the Young's model. This is the length of one wire. So since everything is for one wire, we're going to find this out. So since everything is in parallel, if I find the extension of one wire, I know that all of them would have also stretched by the same amount. In this situation, you will find that the extension comes out as 0.01, I believe. Sorry, 0.1. So this will be 0.1 millimeters. Your answer will be something 0.00 something. But please press the ENG button on the calculator and it will convert this into a power of 3 for you. So this will be option C. Next question is about the energy graph, right? We already understand from O levels the term elastic deformation, elastic limit. Elastic limit is actually from A levels. Let's see what elastic deformation is, where the object, if the load is applied on the object, let's say during loading, you are increasing the force and the extension is also increasing. If you unload or if you start removing the force, it follows the same path back and comes back to the origin. So this is during the unloading phase when you're starting removing the mass from the spring. When it is, let's say, plastic deformation, what has happened is that you've applied so much force that it has undergone plastic deformation. It has permanently deformed, let's say, in this case. So this is force into newtons, this is extension in millimeters, for example. You kept increasing the force and you increase it so much that it has deformed. What will happen in this case? Now, this is during loading. And if you start removing the weight now, it will start coming back following the same path. But notice that there will be a permanent extension, a part of that spring or thread or rubber band that cannot be brought to zero again because you have permanently changed the shape of that system. This is what it will look like. And elastic limit actually goes back to the concept of limit of proportionality as well. So what is this point? This is actually a physical point. So first we encounter the limit of proportionality as L. This is a mathematics problem. Then just beyond this point, we encounter a slight change of path, which is a bit curved than the rest of the graph. There lies a point of elastic limit. Now, this part does not follow Hooke's law, but it still mechanically restrains or tries to regain its shape. If you still go back, if you still start unloading the spring, it will still come back to the original shape. So this actually known as elastic limit. That after that point, after which point is it going to permanently get deformed, right? So even here, this could be the limit of proportionality and this could be the elastic limit. That if, although this is curved, right, it could still come back to the original shape, but it will be unable to do so because in these situations, in these circumstances, whatever strength the metal has, it has already shown that. And if you still pursue by increasing the force, it will then be permanently deformed and be unable to come back. Okay. All right. Then he asks us to understand that the force extension graph or the area under the force extension graph is actually the energy, which is very evident from the axis of the graph. If I want to calculate the cross-sectional area, for example, if I want to calculate the area of the graph, that would be actually force multiplied by extension, or simply y-axis multiplied by x-axis, which becomes force dot E. This looks very familiar to the formula of work done, which was force multiplied by distance. That is why this work done to stretch the spring or to compress the spring is actually stored in the spring and it can be recuperated back. The same thing happens with you when you click the ballpoint and you press the unlock button and it stretches back and the ballpoint goes back into the nib. You're doing the same thing at that situation as well. So he sometimes asks you that why is the energy half generally? So what happens is that the energy that you provide to the system is actually going to be this much. You provided this much force and you provided this much for this much extension. When you got it back, when you got the energy back, this will actually be half of what you've provided. Under the best of circumstances, this is what you are going to get. Another perspective of this is to notice that if, for example, you are applying less force, then you've moved less distance. If you apply higher force, then you move higher distance. So at every point, there is going to be a variable answer of F into D. So combine all of those answers together by an integration formula that you do in mathematics, then you get to this idea again. That is going to have a factor of 1 by 2 half fx, and you can see a formula of half kx squared as well. If you replace f equals to kx, in this formula, you get this one. Okay, now let's see what graphical questions will look like to us. Now it says that it is being loaded. Now these arrows represent that this is actually loading. Loading means that force is being added onto the system. And this arrow means that the force was now being removed, but was it able to come back? No, it hasn't been able to come back. We can see that there has been a permanent deformation in this one. How do we know this? Because now the force is 0, but the length has been unable to come back to 0. He says that what is the net work done on the sample? Net work done will mean how much energy was not received back. It has been wasted. It has been converted into something else. You couldn't get it back when the spring was being stretched or was being compressed backwards. So what has happened in this situation? You applied or you gave the energy. Notice what has happened. Now, this is the amount of energy that you've spent to stretch the spring up to this point. This is the amount of energy that you've spent. That is x plus y plus z. When you were unloading the spring, when you were demanding this energy back from the spring, what has happened? It has only followed the path this point to this point. So the energy received back is this much, which is actually z. So how much energy has been converted into something else? So I get back z, but I've invested x plus y plus z. So I can see that x plus y is the energy that was not given back to me by the spring. Rather, it has converted into the change of shape of the system. So this option will be option B. Okay. Now we move to the mathematical aspect. He says find out the energy of the spring. No problem. Be very careful about the word length and extension. Notice that over here we have extension. Over here we have length. The word is length, which means it's compared from the original length. Notice that this is zero force and it still has the length, which means that when there was no force on the spring, it still had a length of 0.2. When you applied a force of, let's say, 25 newtons in this situation, when you applied a force of 0.25, it became 0.4 meters currently. So now it has a force of 25 newtons and a length of 0.4. So although students memorize that this is going to be the area under the graph, but that is the area under force extension graph. Extension graph. This is length. The only area or the only work done that you've done is actually in this portion. Or you can visualize it this way. So the extension in this situation is going to be 0.2. Notice that this is meters, no need to do conversion. So we're left with 1 over 2, F is 25 multiplied by 0.2. If you solve this question, you are going to get 2.5 joules. So be very careful about this letter length. Now we come to this point again. The same situation has come at this point, but this time this is about compression. He says that the length is 100 when the force is 0. Look at the last point. What is happening in this situation? So what's happening is that, for example, we have a base and we have a spring like this placed on the base. And on the base we have replaced, or we're going to place something. So right now what we've done is we are going to, at this point in time, the length of the spring is 100 because there is no force. The force is absent. Now when you apply a force on the spring, it is going to most definitely come down. He says that what is the energy stored at 70 millimeters, which means that the spring has actually been compressed. The level has come down to, let's say, 70 millimeters. So how much has it stretched? From the original position to the current position, it has been compressed by 0.3 millimeters. Okay. Now at length of 70, total length of 70, I see that this job has been achieved by adding a weight of 6 newtons. What has happened? So I added a weight on the spring. We have added a weight on the spring of 6 Newton and the spring went downwards. The same thing happens in the cars as well and motorcycles as well, that when you sit on them, when you sit in the car, it actually goes down because you applied a weight on them. Okay, so we have applied a force of 6 Newton and the extension, be careful, is 30. So the formula will be 1 over 2, force is 6 and the extension is 30 into 10 raised to the power minus 3 because we want to find it joules, millimeters, should be converted in meters. When you will solve this question, you will get the answer of 0.09 joules. This is option A.